Great, thank you so much, Johannes, for the introduction, and thank you, Johannes and I, for the invitation. I was supposed to be in Nottingham, like non-virtually in June, but this got cancelled, so I'm thankful for this virtual alternative. So my talk is going to be about a joint project with Fatime Mohammadi and Alfredo Nájera Chavez. We posted it on the archive in July, so on the bottom left corner here on the slides, you can find the archive identifier. And the title is Families of Gröbner Degenerations. So I'm going to start with a short overview. I will give you a quick motivation for why we studied these kind of Gröbner degenerations. I will review a bit Gröbner theory. I don't assume you're expert on that particular subject. Then I will give you the construction, our main construction, and the results. And lastly, I will explain an application that has to do with universal coefficients for cluster algebras. Okay, so let's get started. I usually study toric degenerations of projective varieties. And for this particular project, I was a bit intrigued by a certain slogan in mirror symmetry that roughly goes like this. It says, knowing all possible toric degenerations of a variety is equivalent to knowing its mirror dual variety. So this is a very vague statement, but the idea is to study more than one toric degeneration of a projective variety at the same time, and to get close, to get maybe some more information about the variety. And today we're going to be considering a particular case where we want to understand toric degenerations of polarized projective varieties that share a common basis. And I've put this in quotes because throughout the talk we will get to see what this means, or what are instances of this phrase. So let's get started with the background on Gröbner theory. I would be considering polynomials and ideals in polynomial rings all the time. My notation for a polynomial is always like this. A polynomial is a sum of monomials, and if I write this x to the alpha, where alpha is a multi-exponent, then that denotes the corresponding monomial. And now if I take a vector in r to the n, n being the number of variables I have, then I can take the initial form of my polynomial with respect to this weight vector, and it's defined as follows. So I look at all the monomials that appear in my polynomial. I take the dot products or scalar products between my weight vector and the multi-exponent alpha, and then in my initial form I only keep those monomials for which this dot product was minimal among all monomials appearing in F. So similarly, I can take the initial ideal of a whole, the initial ideal with respect to this weight of an ideal, and that's just defined as being the ideal generated by all the initial forms. So in taking these initial forms, I get rid of some monomials. My polynomials get a bit shorter, a bit easier, more symmetric also, and that's the basic idea, the basic concept we will be looking at. For example, very simple example, if I have this polynomial in two variables with three monomials, and I take my weight vector being 1, 0, then I can see, if I compute the initial form, only the first two terms in my polynomial have a positive weight. x2 gets weight 0, so the initial form is just x2. And so this concept of initial form and initial idea can be used to define a Gröbner fan and moreover Gröbner degenerations. So if I start with now a homogeneous ideal for simplicity in a polynomial ring, then its Gröbner fan is going to be r to the n, so n is still the number of variables, and the fan structure will be defined as follows. I say two elements v and w lie in the relative interior of the same cone if the initial ideals with respect to v and w are the same. And I will denote this as v and w lie in C circ. This little circle just denotes the open cone. And with this definition, I can adopt the notation and talk about the initial ideal with respect to a cone rather than some specific element, and that's defined as the initial ideal with respect to an element of the relative interior of this cone. And now the great advantage, or the reason why I am interested in the theory of Gröbner fans and Gröbner bases is the following. So every cone now defines me a Gröbner degeneration. That's a flat family from some normal variety V to the affine space A1 with two types of fibers. If I consider a fiber over a point that is non-zero, it's going to be isomorphic to the vanishing set of my ideal. And if I consider the special fiber, or the fiber over zero, it's going to be equal to the vanishing set of the initial ideal. So whenever I pick some element in R to the n, this actually defines me a degeneration of the vanishing set of J to the vanishing set of the initial ideal. But the initial ideals can be really wild, and not all of them are particularly interesting. So let's look at an example and see what the Gröbner fan, how the Gröbner fan of an ideal looks like. We're going to go to polynomial ring 3 variables and consider this ideal generated by one homogeneous element. So the Gröbner fan now is by definition R3, and the fan structure is the following. So first of all, whenever my ideal is homogeneous, it's not hard to see that the Gröbner fan will contain a linear subspace. In this case, this linear subspace, it's also called linearity space, is generated by the element 1, 1, 1. And you can see, because the polynomial here is homogeneous, if I take the dot product with 1, 1, 1, I will just get the degree in every term. So the initial form of this element is the same as the element. So in particular, this means that my Gröbner fan here is actually two-dimensional times this one-dimensional linearity space. So it suffices to look at the slice where W3 equals 0. And in there, I can identify 3 cones and 3 rays, their intersections. And these are their corresponding initial ideals. So in the relative interior of the cones, I get monomial ideals, the 3 possible monomials that I can obtain as initial form. And in the rays, the initial ideals are exactly generated by the sum of the 2 monomials of the adjacent cones. So this is what a Gröbner fan looks like. And the observation that in the relative interior of the maximal cones, the ideals are generated by monomials is actually true in general. So let's now consider the quotient of the polynomial ring by our ideal J. J is homogeneous, as I assumed before, and we will denote for any tau, any cone in the Gröbner fan, we denote by a tau the quotient of the polynomial ring by the initial ideal with respect to tau. Now, if we fix a maximal cone in the Gröbner fan, as we've seen in the example, then the initial ideal with respect to this cone is generated by monomials. So in particular, we can define the following set. We consider the initial ideal with respect to this maximal cone. So this is generated by monomials. And we define the set BC tau to be the set of cosets of monomials that are not contained in my initial ideal. So a tau here is the quotient by the initial ideal of tau. And in this quotient, I consider those cosets of monomials that do not lie in the initial ideal with respect to my maximal cone. So then in particular, this set is a vector space basis for the quotient a tau. So if I choose for tau the cone C itself, then this statement should be quite obvious, because this is then simply the set of monomials that are non-zero in the quotient. But the interesting observation or the interesting result is that this is also a vector space basis for any of these quotients a tau. And it's called the standard monomial basis, was introduced by Lakshmi Bai and Seshadri for Schubert varieties and then generalized to any kind of ideals by Sturmfeld and White and many others. Now, in particular, I can also take the apex of my cone as a face, 0, and then the initial ideal will be just the ideal itself. and the quotient A tau is just my algebra A again. So in particular, this is the first instance where we have this observation, or where we have the situation that many degenerations, in this case of the vanishing set of J, share one standard monomial basis, right? So all faces of this Gröbner cone C correspond to degenerations of A or the vanishing set of J, and all of them share this standard monomial basis. Okay, so this was the background on Gröbner theory. Maybe I should pause quickly if there's any question. If not, I will just continue with our construction. So what we do now is we take one of those maximal cones in the Gröbner fan, and we're going to define a flat family associated to that fan that incorporates all kinds of degenerations that we find along faces of this fan. So in order to do that, I fix my cone C, and I choose primitive ray generators, or more precisely, representatives of primitive ray generators of C in the quotient. So this is just a little technicality. My cone C itself is not strictly convex, so primitive ray generators are not defined. But if I go to the quotient by the linearity space, then it's a strictly convex cone, and I choose any kind of any set of representatives of primitive ray generators of this cone C bar. And I denote by bold R the matrix whose rows are exactly the rays. And now I can define, for every single element, I can define its lift. So what I'm going to do is the following. I need this little extra ingredient, mu f, that's going to be an integer vector in z to the m. So it has one entry for every row. And I record here the minimum of all the dot products of my array with multi-exponents in f. Right? So this is the same minimum that I took when I compute the initial form of f with respect to those rays. And then I define the lift of f, which is simply given. I mean, if you look at the right-hand side of this formula, this is maybe the more intuitive way to look at it. So I define another polynomial that has now coefficients which live in the polynomial ring over t's. I have one t for every ray, and this lifted polynomial has the same monomials in x's as my element f, but every monomial is endowed with another monomial here, a coefficient in t's, that is given exactly by the product of my matrix R with the multi-exponent, and then I subtract this vector of minimums. Okay, or to compute it, or I don't know, maybe for you the left-hand side of this equation is actually more intuitive. So what I do is I take f, and instead of plugging in x1 to xn, I always plug in xi multiplied with a monomial in t's that I get from my matrix R times the standard basis vector ei. And then in the end, I multiply by the monomial whose in t's whose multi-exponent is this vector of minimums. And I can do this similar. Similar to the initial ideal before, I can define the lifted ideal of J being just generated by all the lifts of elements in J. But in fact, we show that you don't have to run through all elements of J itself. You can actually just look at a Gröbner basis. So a Gröbner basis for J and C is a set of generators of the ideal J whose initial forms with respect to C also generate the initial ideal. So this might be more than just any generating set for the ideal J. And then the proposition part here is that, in fact, this lifted ideal is generated by the lifts of Gröbner basis elements. Okay, so for the construction, and I know it looks a bit technical with these formulas, so we're gonna just do an example to see what this is about. So in our example before, we fixed now one of those maximal Gröbner cones, the one that was purple on the slide before, generated by two rays, R1 and R2, and the linearity space. So my cone C is spanned by these two rays and L. And now I compute the lift. So what do I have here? I can see, for example, the monomial in front of x1 consists of t1 to the 1, this one coming from the first entry in R1, and t2 to the 1, also the one coming from the first entry in R2, so on. The same is true for x2. I have 4 and minus 2 as exponents of this monomial. And then at the end here, I multiply with this monomial that has minus the minimum with respect to the scalar product of each ray as exponents. So for example, for t1 to the minus 4, I can see that when I take R1 and the scalar product between R1 and all these exponent vectors of my monomials in F, then the minimum is 4, and it's achieved for the second and the third monomial. They both get weight 4 with respect to R1. So minus 4 is minus the minimum that I multiply with here. And then I can multiply this out, and it looks like this. So again, the monomials of the lift are in bijection with the monomials of F. The x part doesn't change. I just get coefficients in t's. And now I can start playing around with the t's. I mean, I mentioned a couple of times now already, we're looking at families, so we want to degenerate our polynomial, and we're going to do that by varying the values of t's. So if I set both t's to 0, for example, I get just the third monomial that appeared in F, which coincides with initial form with respect to the relative interior of my cone. And then I can also maybe just set one of those t's to 0. For example, if I just set t1 to 0, what I'm left with here, and t2 to 1, I'm sorry, then what I'm left with is the initial form of F with respect to R1. And the same is true for R2 if I only let t2 vanish. And no big surprise, if both t's are equal to 1, I get back my element F. Okay, and these observations are actually true in general, and that's going to be our first result on the next slide. In case there's no questions, I will just move on. So here's the first theorem. Let's now denote by a tilde the quotient of the polynomial ring in X's with coefficients that are polynomials in T's by the lifted idea. And as before, a tau denotes the quotient of the polynomial ring in X's by the initial idea with respect to the cone tau. And then here's the result. A tilde is in fact a free CT1TM module, and its CT1TM basis is the standard monomial basis with respect to the cone C. So as a free module in particular, it defines a flat morphism by just taking spec of this algebra over the affine space AM. The generic fiber of this family is the spectrum of the algebra A I started with, the quotient by J. And moreover, for every phase of my cone C, there exists an element A tau in AM, such that the special fiber or special fiber over this element A tau is isomorphic to the spectrum of the quotient A tau. And these elements A tau are very simple also. I have this bijection between variables T1, Tm, coordinates of AM and rays R1 to Rm. And if I'm interested in some cone tau, then this is generated by a certain subset of the rays, and I let exactly those variables vanish that correspond to the rays of tau. And the others I just let them to be non-zero. Oops, there's coming up. Sorry, not sure if you saw that. My computer was complaining. Okay, so so this is this flat family, and we've achieved our goal in the sense that it incorporates all the degenerations of my algebra A, or the spectrum of A, with respect to all cones that I can find as faces of this maximal cone C. And in the example, this algebra A tilde would just be the quotient by the ideal generated of the lift of f. So f itself is a Gröbner basis for the ideal generated by f in this case. Okay, so this was so far not really about toric degeneration. So let me take one slide to tell you how toric degenerations come up in the setting. And I apologize if you are familiar with this. Just relax, and the next slide might be more interesting again. So the Grobner fan of this ideal J contains a particular subfan that is known as the tropicalization of J. The subfan has the same dimension as the Kroll dimension of A. So if J defines a projective variety, then this fan is one dimension bigger than the dimension of the projective variety. And in this setting, the tropicalization can be defined as follows. It's the collection of all the weight vectors in R to the n, such that the initial ideal with respect to this weight does not contain any monomials. Right, so if I think about on a scale of how much I degenerate away from my ideal J, and the most degenerate case being monomial ideal, in this case, I stop somewhere in the middle, or well, somewhere on the scale where the most degenerate cases now can be binomial. So if I have a polynomial with many terms, the most degenerate version I can achieve within the tropicalization would be a binomial. And that's very nice because, well, binomial ideals define toric varieties, or more precisely, prime binomial ideals, depending on your convention. And we can find those, if we're lucky, we can find those in the big family corresponding to a maximal cone. And to see that, we now consider the fan that is the intersection of our cone C with the tropicalization. So this is a fan because both the fan structure of the tropicalization and the fan structure of our cone C are given by the Gröbner fan structure. And if I find now some cone tau in this fan sigma, whose associated initial ideal is binomial and prime, then well, the family defined by A tilde contains a toric fiber isomorphic to the spectrum of A tau. Right, so this is how, if I'm lucky, I can find toric degenerations, and this is really not always the case. We will see a bit later for Grassmannians very nice examples where we can find lots of toric degenerations of this sort, but in general, there's no result that would tell you, depending on what cone you choose, that you would actually find toric degenerations in this kind of family. Okay, but we digged a bit deeper and we found out that our family is in fact very closely related to what is known as toric families. So let me go through this construction a bit. If we have this maximal cone in the Gröbner fan, we will denote by xc now the affine toric variety associated to this cone itself. Now, as this is an affine toric variety, by the Cox construction, I can compute its universal torsor, and I will get a morphism from the affine space AM, m being the number of rays of my cone as before, to xc, the toric variety. And there's recent work by Kaveh-Manon that tell us now how to associate a toric family to this cone C in the Gröbner fan. So the construction runs through a couple of steps. First of all, this cone in the Gröbner fan defines a evaluation on the algebra A that is piecewise linear, but the details of this evaluation don't matter too much at this point. Just the important takeaway is that such evaluation defines a filtration of the algebra, and to a filtration I can associate its Rees algebra. And this Rees algebra is like a family that interpolates between the algebra itself and the associated graded with respect to that filtration. So more precisely, the Rees algebra is a direct sum of line bundles over the toric variety. So it is flat over the coordinate ring of my toric variety. And actually, the basis here is again the standard monomial basis with respect to the cone C. But as such a sum of line bundles, the Rees algebra defines a toric family that is now given by the spectrum of the Rees algebra, and the base is given by xc. So a toric family in this setting means several things. First of all, the torus action on the toric variety extends to the total space. And then additionally, we want the fibers to be reduced. To be honest, Kaveh-Manon in their paper, they also assume that the fibers are irreducible, but in order to apply their machinery to our specific setting, we need a bit more relaxed definition. And this will be clear maybe by the following two statements. So first of all, this toric family has a generic fiber, the spectrum of A. But then moreover, if I look at a point in a torus orbit of xc, there's the orbit cone correspondence for toric varieties. So the torus orbits of xc are actually in correspondence with the faces of my cone C. And within the definition of toric family, another assumption is that the fibers over points in the same torus orbit are isomorphic. And moreover, here they will be isomorphic to the spectrum of the corresponding quotient A tau. So A tau again was the quotient by the polynomial ring with respect to the initial idea of J with respect to tau. So, and then here in this second part, you see why we do not have irreducible fibers. If we take a point in the torus orbit corresponding to the interior of the cone C, then this is the spectrum of a quotient by a monomial ideal, so we're very far from having irreducible fibers in this case. Okay, so this family that we've constructed this way, or that we get from Kaveh-Manon's construction, turns out to be very closely related to the family we've seen before. So in the same situation as before, C is still our maximal cone, XC is the toric variety, and PC denotes the morphism from the affine space to the variety XC. Then our flat family, defined by the lifted algebra E tilde, fits into the following pullback diagram. So on the left-hand side here, we have the toric family given by Kaveh-Manon's construction. And down here we have the morphism from the affine space to the toric variety, and the pullback diagram to these two morphisms actually contains our flat family on the right-hand side. Okay, so the methods we've used are very different from the methods Kaveh-Manon used, but it turns out that in the end the families are very closely related, and this is the relation. They fit nicely into this pullback diagram. Okay, so this was the first part of my talk on the general construction and the general results. The second part will now be about the application to cluster algebras. I'm sorry. If there's no questions, I will just move on. Okay. So now we're going to look at universal coefficients for cluster algebras. And don't be scared by these words. I'm going to explain, or at least try to give you an intuition of what a cluster algebra is and what universal coefficients are. So a cluster algebra that was introduced by Fulminant and Lewinsky about 20 years ago is a commutative ring defined recursively by two ingredients. The first one is called a seed. That's a maximal set of algebraically independent algebra generators. And its elements are called the cluster variables. And the second ingredient is a process called mutation. That is an operation that creates a new seed from a given one by replacing exactly one element. And the cluster structure is encoded in a simplicial complex called the cluster complex. So first of all, one thing to note, maybe I've written cluster structure here because in fact, a cluster structure is not an intrinsic property of an algebra. In fact, you can have algebras with different cluster structures defined by different combinatorial inputs. And yeah, we're going to see examples of cluster algebras that you know in a second. So one very famous example is the homogeneous coordinate ring of the Grassmannian 2,5. So we can take the Grassmannian 2,5 with its cluster embedding, and then the homogeneous coordinate ring is this cluster algebra where seeds are in bijection with triangulations of a 5-1. So how does this look? If I have a 5-1 of a triangulation is simply, well, cutting this 5-1 up into triangles. So we're going to fill in arcs in the interior that do not cross, and the maximal number of those. And associated to the arcs of this triangulation, we have the Plücker coordinates. In this case, for example, the arc from 1 to 3 is associated with the usual Plücker coordinate P1, 3. And we also have Plücker coordinates associated to the boundary of this 5-1. And mutation corresponds now to flipping arcs inside this triangulation to create new triangulations of the given one. So for example, I can take this arc that goes from 1 to 3, this diagonal, and I can flip it inside this little quadrilateral. I can flip it to the opposite diagonal to 4, and that gives me a new triangulation corresponding to a new seed. And you can see in this process, if I now again associate the variables to the arcs and the boundary, I've just replaced one Plücker coordinate P1, 3 by P2, 4, and their exchange relation corresponding to the mutation in this case is the Plücker relation between Plücker coordinate 1, 3 and 2, 4. And then I can continue doing this. I can flip the other diagonal, get a new triangulation. Then I can flip again the one, the diagonal 2, 4, the one of 2, 5. And if I do one more flip after 5 such operations, I will end up again with the triangulation I started with. And in this case, these 5 triangulations correspond to the 5 seeds of the Plücker algebra for the Grassmannian 2,5. So more generally, if I consider an arbitrary Grassmannian Kn with its Plücker embedding, then its homogeneous coordinate ring, so that's a quotient of the polynomial ring in the Plücker coordinates or Plücker variables that are indexed by k element subsets of the index set 1 to n, and I quotient by this ideal IKN, that's the famous Plücker ideal. So for this algebra, Scott showed in 2006 that it has the structure of a cluster algebra. If my k is less or equal to 2, then Plücker coordinates are in fact equal to all cluster variables. If k is larger than 3, then the Plücker coordinates are still cluster variables, but they only form a strict subset. And if I limit myself to the cases where either k is 2 or k is 3 and n is 6, 7, or 8, then I get finitely many seeds, as in the example we've seen for the Grassmannian 2,5. If I go beyond these cases, though, I will have infinitely many seeds and then also infinitely many cluster variables. So you can see that Grassmannian 2n and 3,6, 3,7, 3,8 are the only ones where this cluster structure gives me a finite set of cluster variables and a finite set of seeds. Now, why am I particularly interested in cluster algebras? That is because we can use cluster structure on homogeneous coordinate rings to define toric degenerations of the corresponding varieties. So this goes as follows. If we fix a seed for our cluster algebra A, then we can endow the algebra with principal coefficients. So this construction is due to Gross-Hicking, Kiel, and Kron-Savage, where they spelled out the details of these toric degenerations. So what I do, or what I obtain by endowing my algebra with principal coefficients, is another cluster algebra that now does not live only in rational functions on my variables x1 to xn, but it has coefficients that are polynomials in t1 to tn. And with this algebra A prin S, you should think of it as a degeneration of the algebra A, where again t1 to tn are the parameters that interpolate in between my algebra and a semigroup algebra, as we will see. So if I assume some technical, if I add some technical assumptions to my cluster algebra, I have the following. So my algebra A prin S has a CT1TN basis called the theta basis. And it's important to observe here, or to know, that this theta basis is in fact independent of S. So this theta basis is a basis for all these algebras A prin S with varying S. And secondly, now if A was the homogeneous coordinate ring of a projective variety X, then, as I already mentioned, A prin S defines a toric degeneration, and I will denote the special fiber of the toric variety of this degeneration by xs0. And now this is the second time where we observe what it meant on my first slide to share a basis. So all these degenerations for all different S, all these algebra A prin S, they have one basis in common. I can, as a vector space, write them as a direct sum of these theta basis elements. The only difference is always, well, depending on where I am, if I'm at the principal coefficient algebra or the algebra A itself, that I have coefficients in either polynomial rings or just complex numbers, and the multiplicative structure also changes. So, yeah, so A itself in particular has the theta basis as a C basis, and all these algebras A prin S have the theta basis as a CT1TN basis. And the only difference is the multiplicative structure. Okay, so in cluster algebras, the concept of principal coefficients is quite essential, quite famous, but there is another set of coefficients that you can endow a cluster algebra with that has, at least for me, at least even more interesting properties, and these are called the universal coefficients. So I will now assume that my algebra A has only finitely many seeds, and this is to avoid technicalities in the construction of the universal coefficients, as you will understand in just a minute. So we can now endow A with universal coefficients, and this will give me another cluster algebra that lives again in the field of rational functions of x and in variables x1 to xn, but has coefficients in polynomials in t1 to t capital N, where capital N is now the number of all cluster variables. So in particular, if I would drop my assumption here that A has finitely many seeds, I would get infinitely many seeds, possibly, and hence infinitely many cluster variables, and my coefficient ring here would just explode into a polynomial ring with infinitely many variables. This is not impossible. The theory of universal coefficients is in fact developed in this case, but for my application, this will pose complications that I, at this point, want to avoid. So we just treat this case with finitely many cluster variables. And now these universal coefficients are called universal because they have a certain universal property among all kinds of coefficients I can endow a cluster algebra with. I will not explain this universal property, but one consequence is that we have a specialization map for every seed S that is an algebra morphism from the algebra with universal coefficients to the cluster algebra with principal coefficients at my seed S. And this morphism respects the cluster structure. So it sends cluster variables of my universal coefficient algebra to cluster variables of the principal coefficient algebra. So in particular for us right now, having in mind the story about degenerations, this means that this cluster algebra with universal coefficients in fact knows all the toric degeneration. So this specialization map, more precisely, just eliminates those t variables that do not correspond to cluster variables in my seed S. Right? So up here the t's correspond to all cluster variables. So in particular, I can find, if my seed S, for example, consists of the variables x1 to xn, I can find the corresponding t's in this set of all t's, and the specialization map just keeps those t's and sets all others to 1. So in that sense, if I think of the universal cluster algebra, again, as a family of algebras deforming or degenerating my cluster algebra A, then inside here I can find again the algebra with principal coefficients, which gave me this toric degeneration of x to xs naught. But this algebra A unif is still a cluster algebra, and hence it is only defined recursively as all cluster algebras. And this makes it a bit tricky to deal with this universal coefficients in general. In particular, if you want to now get some explicit computations done, yeah, things get a bit complicated. But there is hope to pin this algebra down to a presentation, which we will see now explicitly in the examples of the Grassmannian 2n and 3,6. So I now take my Grassmannian Kn, where k is 2 or 3, and n can be, well, anything or 6, depending on the case. Then I can find a specific presentation of my cluster algebra corresponding to the Grassmannian that is as a quotient by the polynomial ring in all cluster variables. So in the case of Grassmannian 2n, I've already told you that cluster variables are in correspondence with Plücker coordinates. So this presentation is nothing but the usual presentation of the Plücker algebra. So this idea jkn or jk2n is just the usual Plücker ideal I2n. But in the case of the Grassmannian 3,6, we've already seen that there are more cluster variables than Plücker coordinates. In this specific case, there are 2 more cluster variables, which I will denote by x and y. And this ideal J36 is a homogeneous idea, but homogeneous with respect to a non-standard grading, where all my Plücker coordinates, pi, j, k, are of degree 1 in the polynomial ring, but the coordinates x and y are of degree 2. And then the ideal J36 is closely related to the Plücker ideal in the sense that when I take the elimination idea where I eliminate x and y from J36, I get back the Plücker ideal I36. Okay, so I will now tell you our results for these specific cases of Grassmannians. We take this ideal Jkn presenting the Plücker algebra and look at its Gröbner fan. Now inside its Gröbner fan, we identify one specific maximal cone C that has the following properties. First of all, if I apply my lift construction from before to now my ideal Jkn or the algebra Akn with respect to this maximal cone C, then I get a unique, like a canonical isomorphism, between the lifted algebra and the algebra with universal coefficients. And I mean, in both cases, we have seen that the deformation parameters correspond to different things. So for the lifted algebra, I had one parameter, one t, for every ray of C. For the universal coefficient algebra, I had one parameter for every mutable cluster variable, and I identify in this isomorphism, I identify uniquely also coefficients with rays of C. So this in particular means that for these types of cluster algebras with universal coefficients, we have specific presentations. Now, secondly, we've seen that for the lifted algebra, that it has the standard monomial basis as a basis over the polynomial ring in T's. And for the universal coefficient algebra, we have seen, or more specifically the algebra AKN, we have seen that it has the theta basis. And under this isomorphism up here, we actually identify these two bases. The next, I didn't mention Stanley-Reisner ideas or Stanley-Reisner complexes, but for those of you who know, so if I take the cluster complex, that was the simplicial complex that defines the cluster structure or encodes the cluster structure of my algebra, then I can associate to this simplicial complex the Stanley-Reisner ideal generated by square-free monomials corresponding to non-faces of my complex. And this Stanley-Reisner monomial ideal coincides with the initial ideal with respect to my cone C. And then lastly, we have seen that from this construction A tilde, this family of Gröbner degenerations, we may obtain toric degenerations from faces that lie in the intersection of the cone C with the tropicalization of J. And in this case, for every seat, I can identify a specific cone or a specific phase, tau S of C, such that the toric variety that I obtain from principal coefficients for the cluster algebra is isomorphic to the spectrum of the algebra A tau, which was the quotient of the polynomial ring by the initial ideal with respect to tau S. And moreover, I didn't write this on this slide, but moreover, there's also a bijection between all maximal cones in this intersection, so all tropical cones that I can find as faces on my cone C and seeds of S. So I will let this sink in for a second, maybe, also for myself, see if I wanted to say something more. I just realized there's a small typo here. This algebra A tilde in the second bullet point should be A tilde Kn. But yeah, so this is our result regarding the application of Grassmannian 2n and 3.6. And now I just have one more slide that goes a bit into possible further directions. So first of all, we are really optimistic in the sense that we want to extend this application that we now have for Grassmannian 2n and 3.6 to all kinds of cluster algebras of finite type. So graded is one assumption that we wanted here. That might not be necessary, and with frozen directions is another technical assumption, but essentially we are optimistic of exploiting this application to all finite type cluster algebras, so cluster algebras with finitely many cluster variables in particular. And the second direction, or the second further direction is related to a talk that was given by Nathan Ilton a few weeks ago in the same seminar. So he told us in his talk that the type Dn associahedra are unobstructed, which has as a consequence in particular that the Stanley-Reisner scheme of the cluster complex is a smooth point in its Hilbert scheme. So the Grassmannian 3.6 is of cluster type D4. So in particular, this would include the case of the Grassmannian 3.6. The Stanley-Reisner scheme is the scheme defined by the monomial Stanley-Reisner ideal, or by the quotient of a polynomial ring by this monomial ideal, the corresponding projective spectrum of that. And the Hilbert scheme is, of course, the Hilbert scheme of all varieties having the same, or schemes having the same Hilbert polynomial as this Stanley-Reisner scheme. And now Nathan also already mentioned the following corollary in combination with our work, and I'm just now going to mention it again. So in particular as the cluster complex of the Grassmannian 3,6 is this type D4 associahedron. This means that the Grassmannian 3,6, a cone over the Stanley-Reisner scheme, which is in this case exactly the projective spectrum of the algebra that is the quotient of the polynomial ring by the initial ideal with respect to the cone C, and all the toric schemes that are projective spectrum of the principal coefficient algebras A as 0, there are special fibers. To be more precise, all of them now lie on the same component of the Hilbert scheme, and that is because all of them are degenerations of the Grassmannian 3,6. And now one question or one possible direction would be if we could obtain similar results for arbitrary Grassmannians, exploiting their cluster structures, although also I have mentioned before there are some complications arising, as not all Grassmannians are of finite cluster type. So this might get a bit more complicated when we want to study some other Grassmannian, but still we have the cluster structure, and there is some hope to maybe continue in this direction. Now I'm going to leave you with a few references, maybe highlighting in particular the second one here. That is where we summarized all our computational results regarding the Grassmannian 3,6 and yeah, the universal coefficients in this case. Okay, that's all. Thank you for your attention.